This is mathheals.com, where you can find more links to math and computer science YouTube videos. Let's take a look at limits and continuity. Now our definition, limit of a function of two variables. If you remember from before when we just had x's and y's, we looked at studied limit. We had a graph here, and we're studying it as it gets closer and closer to a point. As the x values got closer and closer, the y values got closer and closer. Well, when we're talking about 3 dimensions, and you're looking at it in terms of 2 variables, instead of looking at it just from this side right here, you're looking at it more from coming from a lot of different angles, from a lot of different sides. So you're studying it as it's coming in from here, coming in from here, coming in from here, coming in from here. Actually, infinite number. So it's a little bit trickier to think about. This says let f be a function of 2 variables defined except possibly at x0, y0 on an open disk centered at x0, y0, and let L be a real number. Then remember, it doesn't actually have to be defined at that point because we're just studying limit as we're getting closer and closer. And L's got to be a real number. Then limit as xy goes to x0, y0 of f of xy is equal to L if for each epsilon greater than 0 there corresponds a delta greater than 0 such that the absolute value of f of xy minus L is less than epsilon whenever 0 is less than, and we've got the square root here. This is a circle. So this is what we're dealing with a circle. Now specifically in a circle, we're looking at the distance from the center out to the outer edge here. And this is a distance formula. So we got our xy values out here. And the x0, y0 is the point we're studying, this right here. So this is just finding distance. And again, it's based upon a circle, which is what you see here. And then that's less than delta. Well, let's take a look at a problem dealing with this. Okay, we got limit as xy goes to 0, 0 of x. Wait a minute, 3, 0. Let's try it again. There we go. 3, 0 of x is equal to 3. It says use the definition limit of the function to verify it. Well, if we just looked at this here, not the right side, but here our x value is 3, so you just plug 3 in for x, and that's where they get the 3 at. Now, the x here is our f of xy. The 3 over here is our L. The 3 here is our x0, and the 0 is our y0. So that's how everything maps up. And our formula is the absolute value of f of xy minus L is less than epsilon when 0 is less than or less than or equal to. We'll go look. Lessons. Okay. Square root of x minus x0 squared plus y minus y0 squared is less than delta. Okay, let's start here. Plug in what we got. F of xy is x. So this is x minus L, which is 3, is less than epsilon when 0 is less than x minus 3 squared plus y minus 0 squared. Less than delta. Now again, to solve these particular types of problems, if you remember, we're trying to start with the one on the left, and we're trying to get it to look like this. Well, this absolute value of x minus 3 I can rewrite in this manner. square root of x minus 3 squared. You probably saw this way back when in intermediate algebra if you took the class. But basically, when you got a second power here and it matches your index, the square root and the second power cancel away and just leave you x minus 3. But anytime you have an x coming out of a radical with an even index, then you put an absolute value around it. So these are the same thing. Well, now, this square root of x minus 3 squared I know is less than the square root of x minus 3 squared plus y minus 0 squared. Not less than or equal to, I should say. Because this is my original, the x minus 3 squared, so that's the equal part. But when I add anything squared, well, whatever number I put in here, it's either going to be 0 or it's going to be positive. So it's definitely greater than this over here. And this was less than delta. So if we look at this piece right here and this piece right here, then I can see that delta is equal to epsilon, or epsilon is equal to delta. And that shows our proof. What follows from there. Let's look at the next one. This next one just tries to emphasize that when you're dealing with limits with two variables, then it's the same as when we just had a single variable. We just had x's in there. So in this problem, test limit as xy goes to ab of f of xy is equal to 8, and the limit as xy goes to ab of g of xy is going to equal to 2. And we want to find the limit as xy goes to ab of 3 times f xy times g of xy. Well, when you got numbers in your limit constants, numbers can always just go out in front. So I can put that out in front. And here we got a function times a function. Well, we can split that up. We can have the limit as xy goes to ab of f of xy times the limit as xy goes to ab of g of xy. If you got multiplication, if you got division, subtraction, or addition, you can always split them up into separate limits like this. Well, from up above, limit of f of xy is equal to 8, so this is 3 times 8, and limit of g of xy is 2, which 8 times 2 is 16, times 3 is 48. So that'd be our answer. Let me save this page. Limits and continuity. Page 01.pdf. Okay, let's look at our next problem. We got limit as xy goes to 4, 1 of x squared minus 2xy. Let's take a look at this graph. And you could use WindPlot to do this. I downloaded this trial version of TI Inspire Cast Student software, so I'm going to use it so you can see it better. But if I come down here, if you're not already there, press your home button. And you should be back to here. And then you can choose this one down here that looks like a graph. And it'll get to this point. Press your menu button, choose View, and choose 3D Graphing. Now down here, and your cursor should be down here, and we're wanting to put in x squared minus 2xy. So I do x, char 2, and I'll do my right arrow key to go out of the exponent mode. Minus 2, was it 2xy? Yeah. And I'll press enter. That one wasn't very good. Well, assuming I did it correctly, let me check. X squared minus 2xy. Didn't appear to graph at all, did it? Yeah, I don't see it. I made these problems up, so maybe that one doesn't come to... Well, there should be something there, though, I think. Let me try WindPlot. I don't have my other flash drive plugged in, so let me go ahead and plug that in. I still have yet to find a good tool for graphing 3D. It's cheap. Not that this software would be cheap. If I end up buying it, it'll be $150. Which I'm giving serious thought to it. And if I can get this to recognize. Try one more time. Usually a third time's the charm, but... Oh well, it doesn't look like that's going to come up. It's going to be a day when nothing's going to work. But anyway, these are nice polynomials. We got x to a power, y to a power, so there's nothing wrong with this one. So let's plug in. When we got the limit as xy goes to 4, 1, the first part is your x, and the second part is your y. There you go. Talk about slow. Oops. Get there eventually. Here we go. Peanut. And I'll bring up WindPlot. And again, this is so small you can't see it, but I'm going to tell you what I'm doing. I'm choosing window, 3 dimensions. I'm choosing equation. I'm choosing explicit. And I'm going to type in x char 2 minus 2xy. And I'll click OK. Let me do view axes. Okay, and we're studying it as it goes to 0, 0. Oh, wait a minute, not 0, 0. 4, 1. So if I were to put a point on here, let me see, equation, where's point? Point, Cartesian. This would be 4, 1, and 0 for z. So 4, 1, 0. And click OK. And that might have been too small. Let me do an edit again, choose solid, and I'll make this one 4. There it is. Now see how our graph just stops there? That doesn't actually get... I wonder how I screwed it up. Zoom. View. Zoom. Page down, page up. Rotate. Up, down, left, right. Okay. Observer. In, out, far out. Insert, delete. I wonder what that does. Let me see. Now, not what I want. But you can see the graph is coming. And it doesn't appear to have any problems. I'm not quite sure why this This package over here didn't have that. Not a real great indication of the package. Maybe I shouldn't buy it. Anyway, it's fine. So we're just going to go ahead and plug this in for x and plug this in for y. So let me label those again. This is your x and this is your y. And we have 4 squared minus 2 times 4 times 1. So that gives us 16 minus, and then 2 times 4 is 8. So we got 16 minus 8, or 8. Now these are kind of tricky if you don't have a good package to look at the graphs on. And we'll see that in some examples. Let's take a look at this one. Got limit and by the way, I was talking about the where this is continuous, but I didn't actually write it down. So let me write it down in that one. It's kind of throwing me off with that bizarre graph. Okay, so we're looking at our where it's continuous. And this will be for the set of all xy values such that x is a real number and y is a real number. So that's where it's continuous. Because this is a polynomial, and I said, these are nice polynomials. They exist everywhere. We don't have a problem. Okay, limit as xy goes to 5, 2 of x squared over y minus 1. Okay, now let's graph this and just see how poor of a job it does on this one. Okay, if I press home, that's always starts you off at your beginning. You can click the graph button down here, then choose your menu, choose view, choose 3D graphing, and we got x squared, so x caret 2, I'll right arrow to get out of the exponent, divided by, and then beginning parentheses, y minus 1. Looks like it put the closing parentheses on there for me, but if yours doesn't, then you'd need to put it. That looks better. Okay, so we got this. Now, there's one place where we have a problem with this, and if we put 1 in for y, we get 1 minus 1 in the denominator, which is 0, which we'll talk about in a minute with our continuity. So this graph doesn't exist at y is equal to 1. Well, if I come here, here's your y-axis, here's 1, and you see it puts a gap there. Now this TI Inspire CAS puts a pretty big gap, and I've noticed that whenever it's undefined somewhere, it makes sure that you know it. This is actually defined at 1.1, which from this graph it looks like, well, it's not defined at 1.1 either. It's not defined at 1.05 and so forth. But it just wants to make sure you see where the gap is. So as I look at this, we're studying limit as xy goes to 5, 2. Well, if I think where 5 is, 1, 2, 3, 4, 5, so be somewhere over there on the outer edge, and 2, here's looking at it in terms of the x and y, 5 and then 2, it's actually defined there, and I don't see anything that really throws it off for a limit. What would throw it off is if we were to find the limit at 0, or not 0, 0, but at 0, 1, for example. Well, the graph doesn't exist at 1, and coming from two different sides, we might see that it gives us two different values. One's going to this, one's going to that. It doesn't for this because it looks like they're all converging upon this one place right here. But again, you have to be careful about that. Okay. So to find our limit, it's as simple as just plug in the values. Put 5 in for x. So we've got 5 squared, and then put 2 in for your y, so 2 minus 1, which gives us 25. Now we got a fraction. Whenever you have a fraction, set your denominator equal to 0, and then solve it. And we get y is equal to 1. This is the area that causes us a problem. So for our continuity, it's continuous at all x, y values such that y is not equal to 1. Now, you can also put, if you want, x is any real number. Or you can, some books may just assume that, and that's put y cannot equal to 1. Okay, let's look at this one. Get limit as xy goes to 1/4 pi of x squared sine xy. Okay, now for our limit to exist, we can't have any weird things going on with it. And usually your weird things happen when you got possibly rational functions. Like up here, if we were, we said we have a problem at, then this is rational. We have a problem at 1. If instead of the x and y here, if y was 1 and then x was whatever, we might have an issue there. It all depends. Now here, sine doesn't have any places where it's undefined. It goes along smoothly everywhere. X squared doesn't have any problems. And I can put anything in for x and y on this. So we should be fine at just plugging in our values. Okay, so put this in for x, put this in for y. So we got x squared, so we got 1/4 squared sine of 1/4 times pi. That gives us 1/16 sine pi over 4. And if we look in our unit circle, pi over 4, which is right here, the point is the square root of 2 over 2 and square root of 2 over 2. Sine is our y part, which is square root of 2 over 2. So we're going to have 1/16 times square root of 2 over 2, which gives us square root of 2 over 32. And that would be our limit. Okay, now talking about continuity. We said that x squared is a polynomial. That's nice everywhere. No place is undefined. And we said we can plug anything in for sine. So for our continuity on this, we have the set of all xy values such that x is any real number, and y is any real number. By the way, another way to write that is where you put that symbol right there for a real number, in case you see that in books. Let's save this. It's pretty disappointing on that first graph. I couldn't get that calculator to graph that one. Oh, let me try this one, because I'm just curious now. Okay, so if I press my menu, it'll take me, oops, sorry, I lied to you, home. Take me back here. Then I choose the graphs here. And it puts a new one across the top here, so you can see that. But if I chose menu, choose view, choose 3D graphing. This one's going to be x squared, so x caret 2, right arrow to get out of the exponent, sine of xy. And press enter. That's nice. Love a software that doesn't do anything. Let's go look at WindPlot. Close that. Do window, 3 dimensions. Choose let's see, equation, explicit. And this was, what was this? X squared. So x caret 2. Times, I'll do an asterisk, sine xy. And click OK. So far, WindPlot's winning out. So that's our graph. Interesting. Now, sometimes when it looks like it just stops, remember it keeps going forever. Just WindPlot doesn't keep going forever. Okay. And let's take a look at the next one. It says find the limit and discuss continuity of the function. Limit as xy goes to 2, 2 of arcsine x minus y. Well, now to find the limit, well, what we're going to do is we'll plug this in for x, plug this in for y. So we got arcsine of 2 minus 2, which gives us arcsine of 0. Now, we don't know what this value is, so we can set it equal to a variable. Say p is equal to arcsine. If you remember from trig, we can take sine of both sides. And sine and arcsine cancel each other out, and we get sine is equal to 0. Now, arcsine, inverse sine, is valid from negative pi over 2 to pi over 2. Right here, angle-wise. So if we look where sine is equal to 0 at, sine is our y, that's going to be at 0. So p is going to equal to 0. So that's our limit. Okay, let's talk about the continuity, where it's continuous. Now, if I look at y is equal to sine x, specifically just looking where it ties directly to arcsine, this bounces back and forth on my y's from negative 1 to positive 1. Oops, I guess I ought to put y there if I'm going to say that. And on my x, I'm going to go from negative pi over 2 to pi over 2. Like that. Now when we're talking about arcsine, which is the inverse of that, these flip. This is my range on this, so it becomes my domain over here. So my x values are going to go from negative 1 to 1. And then my y values will go from negative pi over 2 to pi over 2. Well, this is a little bit different when we're talking about multiple variables. This is your domain right in here. So our domain is from negative 1 to 1. So we're going to have negative 1 is less than or equal to x minus 1, which is less than or equal to positive 1. And if you remember from college algebra, that looks like the formula for the absolute value inequality. So that's going to be absolute value of x minus y is less than or equal to 1. So for where it's continuous at, we're going to have, there we go, set of all x, y values such that the absolute value of x minus y is less than or equal to 1. And I'm not going to write it down to x and y are real numbers, but that's where it's continuous at. If you look at it, it's continuous. 2 minus 2, that's okay, isn't it? 2 minus 2 here is 0, which is less than 1. Okay, let's look at this one. Got limit as x, oops. Limit as xy goes to 0, 0 of x squared minus 9y squared over x minus 3y. Well, first off, let's graph these on our our different packages and see how they fare. I'm going to click the X to close that. No, I don't want to save that. I'm going to choose the new graph there. And when it comes up, then I'll press Menu, choose View, 3D Graphing. And this one, I'll put parentheses on top. So I got x squared. I do x caret 2 minus 9y caret 2. Right arrow to get out of that. Right arrow again to get out of the top parentheses. Divided by parentheses around the bottom, x minus 3y. And enter. That's nice. I wonder how I zoom in. Oh well, I think we can see it. As it's approaching 0, 0 from all the different sides, they all appear to be going to the same value. So we're fine there. That'll make more sense, I think, after the next example. Now this one has some algebra we can do. Limit as xy goes to 0, 0. We can factor the top part. Difference two squares, so this factors as x plus 3y times x minus 3y. And after I do that, I notice that the x minus 3y is going to cancel. And we're left the limit as xy goes to 0, 0 of x plus 3y. Now we can just plug in our values at this point. So put 0 in for x, 0 for y. Remember, this is x, this is y. So we got 0 plus 3 times 0, which gives us 0. Which is what it looked like from the graph. It looks like that's what they're approaching on. But here we have a fraction. And with a fraction, we're going to talk about our continuity. We cannot have the denominator equal to 0. So I'll set the denominator equal to 0. And then if I solve this, I get x is equal to 3y, or you could have y is equal to 1/3 x. And it's going to be continuous at all xy values such that x cannot equal to 3y. And we got some different gaps in our graph here, and that kind of indicates to you where you know, the places where you can't have. And again, it does an exaggerated view in this. X and y are still real numbers, but that'd be our continuity. Okay, number 8. Got limit as xy goes to 0, 0. The square root of x times square root of y. Now in Calc 1, pretty well, if we could plug in the number for our limit, then we're happy. You know, it's fine. Here though, if I put 0, 0 in here, I get square root of 0 times square root of 0, which gives us 0. No problem there. Except this one, like I say, sometimes you really have to be able to look at the graph to see what's going on with it. And I printed off the graph here so I can show it in the class. But if you look at this, can't rotate it, but here's 0, 0 in the middle, and coming from all these different angles here, it's all approaching the same value, but it isn't approaching from this side, is it? So it's not coming at all. And the limit only agrees if it's approaching the same value from all sides, from all angles. And actually, if I think about it, I can't even put negative values in here for x and y, can I? So it can't be coming from the negative side. So this limit does not exist. So these are a little trickier than the normal limits we're used to. The normal limits, you just plug in your numbers and you're happy. In case the problem's up above, you're sitting there, why is he even looking at this? Why doesn't he just plug in the values? Well, you can't assume that. Now, most of the times you'll have something weird going on, like you'll have a rational function, you'll have a radical with an even index, tangent, secant, places where it's undefined, where possibly it's coming from this side, it's going to a different value than the other side. Okay, let's look at this one. This is another one of these oddball ones. I'll put it up here. The limit as xy goes to 0, 0. And if I, for of 1 plus y over x plus y. Okay. Now, if I look at just the x and y axis here, here's 0, 0, of course. It has to be approaching the same value from all different angles. So you got infinite number of angles you got to worry about. And I'll give you a hint here. It says think along y is equal to 0. If you set one of your variables equal to 0, well, y is equal to 0. I'm looking at it as it's coming from this side and from this side. Well, think about it if I put 0 in for the y, because if I looked at it along this line here, y is always equal to 0, isn't it? We're going to have limit as xy goes to 0, 0. And if I put zeros in for the y, I'm looking at it as like 1 over x. Well, if you remember what the graph of 1 over x looks like, looks like this. So coming from the left side, it's going down to here, and coming from the right side, it's going up to here. They're not agreeing coming from the left and from the right, if I look at the x's, which means that this limit does not exist. Now this one, you might look, well, I could see that because I put 0 here and 0 here. But that isn't necessarily the case, because remember, your limit does not have to actually exist at that point. You're studying it as it gets closer and closer. So if you see an obvious one like here, where you have square root of x, square root of y, and so forth, then that's kind of, you can think it through. But sometimes you just try to plug 0 in for y, 0 in for x. It's the same way as I'm studying it here. If I study coming along the y-axis, approaching a value, they should approach the same value. Okay. Let me save this, and then we'll look at this next problem. This shows you how to think of the continuity of a piecewise function of multivariable. And as usual, I drank too much pop. That's just great. You think I'd be a little smarter than keep doing it over and over. Okay, so we got 9x to the fourth minus y to the fourth over 3x squared plus y squared. And then 0. Now these are the z values. So remember, f of xy is like your z. The z is equal to this and equal to this. When the first one, when xy is not equal to 0, 0. And this one, when xy is equal to 0, 0. Now, not what this picture looks like, but in general, what we're talking about is we got some kind of three-dimensional shape. Let's say I got a plane. Three-dimensional shape. And it's got a hole in it here. So that's what does not equal to 0, 0. It looks like this, except for where you have the hole. And then the hole can either be filled in by this other one, so I could have this filled in right there, and then it's continuous everywhere. Or I can have a plane with a hole in it, and this other piece right here could be up here, which means it's not continuous at that point. Okay, so discuss the continuity of the functions f and g and explain any differences. Well, obviously 0, 0 is where I have a problem, because if I put 0 in for x and 0 in for y, I get a 0 in denominator. So the question is, do these approach the same, are they equal to the same value? They approach the same value when we're talking about limits. Well, this top part here factors. So 9x to the fourth minus y to the fourth is the difference of two squares. That's 3x squared plus y squared over, times 3x squared minus y squared over 3x squared plus y squared. That's this top piece. So if I factor the top, I see that this cancels with this, and I'm left with 3x squared minus y squared. Now again, if we put the 0 and 0 in for the x and y, I see this equals 0. And obviously the other one gives you 0. Since these are the same, that means this is first case, where you got one three-dimensional shape and then this other one here fills it in. Now this one isn't defined there, because remember, but what we're doing is we're studying the limit. I didn't write it all out here, but we're actually looking at the limit as xy goes to 0, 0. This is not defined at 0, 0. Since these are the same, then for f of xy, for a continuity, this is continuous. The set of xy values such that x is a real number and y is a real number. It's continuous everywhere. Okay, let's look at our other one. G of xy is equal to 9x to the fourth minus y to the fourth, 3x squared plus y squared, and 2. And this is when xy is not equal to 0, 0. And this one's when xy is equal to 0, 0. Well, remember we looked at the limit of the top part, and that was the limit as xy goes to 0, 0, 3x squared minus y squared, and we said that was equal to 0. Well, if we look at our second piece here, well, that's 2, isn't it? These don't match, which means it's discontinuous at that point. So our continuity, the set of all xy values, I won't write down that they're real numbers, but the set of all xy values such that xy cannot be equal to 0, 0. So it's not continuous at 0, 0. It's actually a removable discontinuity at 0, 0. Because this cancels away, and it's this case up here where your point is up here. Let me start a new page, then we'll look at this problem. There we go. Number 11. Limit as xy goes to 0, 0 of 3x squared y over x squared plus y squared. Okay, now I've been alluding to the difficulty of finding limits on these, because you just can't simply just plug in the values, because we're looking at come from an infinite number of directions. Now, you don't actually have to, usually looking at signs handles most of them. But one technique we have is we can switch things to polar and see if that helps. Well, if you remember from trig, we had cosine theta is equal to x over r, and sine theta is equal to y over r. Now I can multiply both sides by r here, and we get x is equal to r cosine theta, and y is equal to r sine theta. So this is how we'd switch it over to polar. And it tells you that in the instructions here. And note that as the limit as xy goes to 0, 0 implies r goes to 0. So when we convert this over, this since this goes to 0, 0, then r is going to go to 0. When you think about it, it makes sense. Because here's 0, 0, and out here, this is a circle, isn't it? If this is 5, as I come in to 0, 0, in terms of a circle, the r is approaching 0. Okay, so then I'll put, for x, I said that was r cosine theta. For y, that was r sine theta. Now down here, if I plug those in, I can work down the math and do it. But we also remember that r squared is equal to x squared plus y squared. So this x squared plus y squared down here becomes r squared. Well, up on top, r cosine theta squared gives us r squared cosine squared times r sine theta over r squared. Well, these r squareds cancel, and I got 3 cosine squared theta times r sine theta. Now, if we plug 0 in for r, I'm going to have 3 times cosine squared theta times 0 times sine theta. And 0 times anything is 0, so that gives us 0. Now this next one wants us to use polar coordinates and then use L'Hopital's rule. So let's take a look at that. So we've got limit as xy goes to 0, 0 of 6 sine of x squared plus y squared. In case you're wondering, these problems really work out nice when you got x squareds plus y squareds in them. And when it's approaching 0, 0. Okay, so I can rewrite this. Limit as r goes to 0. And I got 6 sine. And remember, x squared plus y squared is r squared. So we got sine of r squared over x squared plus y squared is r squared. Now if I put 0 in here, I'll get sine 0 squared, and sine of 0 is 0. If I put 0 down here, I get 0 squared, so that's 0. So we use L'Hopital's rule. L'Hopital's rule says take derivative of the top, derivative of the bottom. 6 remains there. The derivative of sine is cosine, but this is a chain rule. Since we got more than a single r in here, we have to multiply times the derivative of the r what's inside the parentheses, times the derivative of the r squared. On the bottom part here, we're going to have the derivative of r squared. Now you notice, chain rule up on top. The derivative of sine is cosine, and then we had to multiply times the derivative of what's inside the parentheses. Once I do that, I see that these match. I don't even need to find derivatives. Those are going to cancel. And we got limit as r goes to 0 of 6 cosine r squared. Now if I plug in my 0 now, I'm going to have cosine of 0 squared, which is 6 times cosine of 0. And cosine of 0 is 1. So that would give us 6 as our answer. So a lot easier to find on those particular ones, though they are very specialized with those conditions, but a lot easier to find using polar. Next type problems want us to discuss continuity of the function. Okay, and we're going to have f of xy z is equal to z to the third over x squared minus y minus 5. Well, this, instead of doing 3 dimensions, we're talking about 4 dimensions here. But it's still the same idea. When we got a fraction, we can't have the denominator equal to 0. So let's go ahead and set it equal to 0. So we got x squared minus y minus 5 equal to 0. Take the negative 5 over, and basically x squared minus y cannot equal to 5. So you could write this different ways. It's continuous for the set of all x, y, z values such that x squared minus y is not equal to 5. Now x, y, and z are still real numbers. I'm not going to write that. But now I've shown fractions over and over here, so let me talk about some other types. And I'll just do these in 2 dimensions. or 3 dimensions, sorry. If we have f of xy is equal to square root of something, radical with an even index. Well, you can't have negative numbers inside of a radical with an even index, so what we do is we take what's inside and we set it greater than or equal to 0. So for like here, for my continuity, this would be the set of all x, y values such that x minus y is greater than or equal to 0. If we had a log of some sort, and it doesn't matter what you put in there, but let's say x squared y. Can't have log of 0 or log of negative number, so we'll take what follows our log and we'll set it greater than 0. Can't be equal to 0. So then here, this would be the set of all x, y values such that x squared y is greater than 0. So again, when you're thinking about where something's continuous, you have to think about your rules for continuity when you had just x's and y's, and then you just apply it accordingly, and it's still the same idea. Okay, let's look at our last problem here. This one is to find each limit. We're going to see this formula again in the next section, next lesson. Okay, 3x squared minus y squared. In our first one, we'll find limit as delta x goes to 0 of f of x plus delta x, comma y, minus f of x y all over delta x. Okay. And in order to plug it into this formula, we need f of x y, which we're given. We also need this. So let's find f of x plus delta x, comma y. Now, we're going to plug this in for x, and we'll plug this in for y. So we go back to our original function, and we'll plug the x plus delta x in for x. So I got 3 times x plus delta x squared minus, now plug y in for y, so that just gives us y squared. So we got 3 times x plus delta x times x plus delta x minus y squared. 3 times x is x squared, x times delta x is x delta x. Delta x times x is x delta x, and delta x times delta x is delta x squared minus y squared, which gives us 3 times x squared plus, these are the same, so I add numbers in front of them, so that's 2x delta x plus delta x squared minus y squared, which gives us 3x squared plus 6x delta x plus 3 delta x squared minus y squared. And now we're ready to plug in our formula. Well, this f of x plus delta x y is this right here, so I'll plug that in. So I got 3x squared plus 6x delta x plus 3 delta x squared minus y squared minus f of xy, which is this up here, which is 3x squared minus y squared. Notice I put a parentheses around it because that minus has to flip the sign of everything. So then this becomes a limit as delta x goes to 0 of 3x squared plus 6x delta x plus 3 delta x squared minus y squared, and a negative in front of parentheses flips the sign of everything inside. So this becomes a negative 3x squared plus y squared all over delta x, which gives us limit as delta x goes to 0. Combining the like terms, 3x squared minus 3x squared drops away. Negative y squared plus y squared drops away. So we're left with 6x delta x plus 3 delta x squared all over delta x. Now notice everything up on top has a delta x, so I can factor that out. And that's going to leave us 6x plus 3 delta x over delta x. Well, now we have delta x times something up on top, and we've got delta x down below, so those delta x's cancel. Only reason you can do that is because they're it's multiplication up on top. So then we're left with the limit as delta x goes to 0 of 6x plus 3 delta x. And we can now plug 0 in for delta x because we don't have delta x in the denominator anymore. So we've got 6x plus 3 times 0, which gives us 6x. And that's our answer. Okay, let's look at B. B says the limit as delta y goes to 0 of f of x plus, or x, then y plus delta y minus f of xy over delta y. Let me double check the formula. Yeah. Okay. Well, to do this limit, we need this right here. So let's find that. F of x y plus delta y. I'm going to plug this in for x, and I'll plug this in for y into my original function. I don't remember what my original function was, but let me look. 3x squared. So I got 3, and put x in for x, so it remains 3x squared, minus y plus delta y squared. So I replace the y with y plus delta y. So that gives us 3x squared minus y plus delta y times y plus delta y equals 3x squared minus y times y is y squared, y times delta y is y delta y, delta y times y is y delta y, and delta y times delta y is delta y squared, which gives us 3x squared minus y squared. Since these are the same, you add the numbers in front of them, so that becomes 2y delta y plus delta y squared. And a negative in front flips the sign of everything, so this becomes 3x squared minus y squared minus 2y delta y minus delta y squared. And now we're ready to plug into our formula. So f of x y plus delta y is equal to all of this. So that's 3x squared minus y squared minus 2y delta y minus delta y squared minus f of xy, which was 3x squared minus y squared over delta y. Well, again, negative in front of your parentheses is going to flip the sign of everything inside, so all the rest of this just carries down. And then this becomes a negative 3x squared plus y squared over delta y. Combine together like terms. 3x squared minus 3x squared drops away. Negative y squared plus y squared drops away. And we're left with the limit as delta y goes to 0 of negative 2y delta y minus delta y squared over delta y. Now the problem is the delta y downstairs, because if I plug 0 in for that, I'll get 0 in denominator. So that's what we're trying to eliminate. I notice up on top everything has a delta y, so I'll factor that out. And that leaves us negative 2y minus delta y. Now these delta y is going to cancel. And we got limit as delta y goes to 0 of negative 2y minus delta y. And now we can plug 0 in for that. So that's negative 2y minus 0, which gives us negative 2y. And that's our limit. We're going to actually see that's our derivative formula we'll use in the next section or lesson. So let me go ahead and save that. I think that was the last problem. Time for my tablet to blow up too. Yeah, it was the last problem. So I'm going to go ahead and stop the recorders. And I apologize for that difficulty with the graph at the very beginning. have no clue why the TI Inspire cast wasn't doing that one right.